Every answer you get from an AI is computed on a GPU, a graphics processor, or at Google on their own chip, a TPU. Both are built to do staggering amounts of arithmetic, and both spend most of their time doing absolutely nothing. This is a race between 95 of them, and it comes down to one number. The first number is arithmetic. A flop is one single operation, one multiply or one add. Flop per second is how many of those a chip gets through, and a modern GPU does quadrillions every second. This is the number the industry advertises. The second is bandwidth. Those numbers being multiplied have to be pulled out of memory first, and bandwidth is how many bytes per second the chip can drag in. Here is the asymmetry that drives everything. Adding arithmetic to a chip is cheap. Adding bandwidth means more pins, more power, more cost. So it grows far more slowly. Divide the first by the second and you get one number, flop per byte. How much arithmetic this processor must do for every byte it fetches just to stay busy. If it climbs, the chip finishes the maths and waits. One bar is one GPU or TPU, and a bar never moves once it ships. We start in 2010. The tallest bar here is the GeForce GTX 280, released 2 years earlier, and it needs 4.5 calculations for every byte it fetches. That is a balanced machine. Feed it and nothing sits idle. The GTX 580, twice the transistors and the number doubles to 8. The arithmetic doubled. The memory did not. Nothing dramatic yet. This is still the era when a graphics card was mostly a graphics card. But watch the direction. There is only one and it is up. Memory got faster in these years too, just nowhere near as fast as the arithmetic did. The Tesla K20, NVIDIA first card sold for computation rather than pixels, and the number doubles again. And once you sell a GPU for maths, the incentive is obvious. Add more maths. More arithmetic units fit on every shrink. Wider memory buses do not. So the gap widens quietly, generation after generation. The K80, 8 times the 2008 number, and still nobody is calling it a problem. Here is the thing. Every one of these bars is a GPU that got faster. Every one of them also got harder to feed. Still nothing anyone would call a wall. 8 years in, and the curve is still gentle. If the story stopped here, there would be no video. This is a well-engineered piece of hardware doing exactly what it should. Then the P100, an NVIDIA first attempt at fixing it. Stacked memory, sitting on the same package as the chip. It helped, look how little. And then this, the V100 and the arrival of tensor cores. Silicon that does nothing but multiply matrices, thousands of numbers at a time. The arithmetic goes up roughly 8-fold. The memory does not follow. The bar quadruples in a single generation. That is the moment the wall appears, not gradually, in one product cycle. And it is the same moment deep learning gets cheap, which is not a coincidence. Tensor cores are what made it cheap. The T4, a small card you can slot into any server, and it is near the top of the board. Notice what never happens on this chart. NVIDIA never loses its position as the largest manufacturer. The bars never fall. They cannot fall. The flop per byte ratio is a property of the silicon. Once a GPU ships, its bar is fixed for the rest of its life. So this race has no comebacks and no strategy. It is decided entirely by who shows up. The A100, the GPU that trained most of the models you have heard of. And now the board starts filling in from everywhere at once. 2021, and the lead changes hands. Google's TPU version 4. A TPU is not a graphics chip at all. Google designed it in-house for one job, and it is now the most arithmetic-heavy processor here. Then Cambrican in China. The H100 arrives, the most wanted chip on Earth for 2 straight years. And a gaming card, the RTX 4090 in somebody's desktop, which is higher than the H100, a card built for video games, beating the most expensive processor in the data center. Sit with that for a moment. The L4, a small inference card, the kind you put in a server rack by the dozen, and it goes straight to the top of the board, above every training GPU on Earth. 16 new processors ship in 2023 alone. Everybody is building one now. AMD, Intel, Amazon, Huawei, Tesla, Meta, all of them shipping their own accelerator and all of them landing high on this board. And here is the record. Google's TPU v6e, 560 calculations for every byte it can fetch. Against 4.5 at the start of this video, 127 times hungrier. Now look at the shape of the top of this board, because this is the part nobody expects. You would assume the giant training GPUs are the most extreme, the flagships, the ones that cost more than a car. They are not. The H100 sits 11th, the A100, the GPU that trained the models that started all of this, 33rd of 95. The most starved processors here are the cheap ones, the little inference cards and a gaming GPU. Because the expensive chips got the expensive memory, stacked and welded onto the package. The cheap ones got the arithmetic and ordinary memory, and then were sent out to answer billions of questions anyway. So the processor most likely to be replying to you right now is not one of the well-fed ones. It is one of the worst. Which is the twist. The memory wall is not worst where we train these models. It is worst where we actually use them. So let's turn the whole board upside down and look at the processors that were easiest to keep fed. The lowest flop per byte we ever shipped. Every GPU at the bottom of that board is old. Every one at the top is new. We did not build faster processors. We built hungrier ones and then we stopped feeding them. And the worst of it is not in the supercomputer. It is in the cheap little card answering your question. So what breaks first? The memory or the money? Tell me in the comments.